So we are right on time. I hope you all had a good lunch and coffee. If not, we still have coffee outside. But yeah, welcome to the afternoon session about flexibility. And so I'm happy to introduce our first speaker, Katerini Foroli, talking about AC flexibility.
Hello, I'm Katerina Foroli. I'm here representing the nominated electricity market operator of Greece, known as HENEX. And I will present to you our proposal for the design of an AC feasible local flexibility market with continuous trading. So the team of this study consists of some people from the business sector. These are the research team of HENEX, and from the academia, two professors from the Aristotle University of Thessaloniki. So the motivation behind this research was to give an answer to the operational challenges of the distribution system. These are caused by the increased loading of the system and the increased participation of theirs on it. Thanks to the new technologies, DERs and flexible consumers can now participate in the market, and this gives us new tools to prevent or alleviate the DSO operational challenges, like, for example, local flexibility markets for flexibility trading. So various design approaches of LFMs have been proposed. These are mainly different in terms of time frame, time of flexibility offered, clearing methodologies, and level of network awareness. So each approach has its own advantages and disadvantages, so we will see what our approach proposes. So we build here an AC feasible, a local flexibility market with continuous trading. The market is AC feasible as it considers the distribution system constraints. It supports continuous trading. This is better for the liquidity of the market and so as the trades to be closer to the physical delivery. And the market also supports partial matching of bids. This is also crucial for the liquidity of the market. And also our market has the minimum requirements for information exchange between the DSO and the market operator. And the implementation is computationally light, something that is crucial again for the continuous market. So, the general structure of the market is that the market, first of all, operates after the day-ahead market. So the trading gates open after the DRAM for all market time units and closes for each market time unit 1 hour before the physical delivery. So market players can place their order continuously for any market time unit of day D. And the market time units can have any duration from 15 minutes up to an hour. So the goal of our LFM is to solve line congestions. And so we trade active power flexibility, and the actors who participate in our market are the DSO, the market operator, and the market participants. So let's see the responsibilities of each actor. The distribution system operator is the one who performs periodically the forecasts for the non-dispatchable generation and consumption. In that runs the AC power flow simulations for the market time units, and in case of a network constraint violation, he communicates the essential network data to the market. Now the market participants are actually flexibility service providers. They own dispatchable assets, for example, dispatchable generation, storage, or responsive loads. They submit sell or buy orders of active power. Their participation is asset-based, and in case of a trade, then the day-ahead market schedule of them is modified. So we see here also the essential information for an order. And the one who develops and operates the market is the market operator. The market operator clears and settles the transactions and checks for the feasibility of the trades based on two conditions. The first one is the financial feasibility. So trades here are only allowed between orders of different direction, a buy and a sell order, which are located in different nodes. And then the price of the buy order must be larger than the price of the sell order. And for the network feasibility, existing violations must be solved or alleviated, and then we must not have any new violations in the system. And in case of a feasible bid, then the bid is cleared in a price, that is the price of the order that was submitted first. And this is in line with the rules of the European intraday continuous market known as XBID. So here we will see the general concept for mitigating the grid issues. So as we will expect, the trade changes the nodal voltage magnitude and the line apparent power flow. And these changes are calculated here based on the sensitivities of the grid state variables with respect to the nodal active power injections. So these sensitivities are dependent on the network operating point. And because of that, they are calculated every time a new forecast is made by the DSO or a new trade is concluded. We must also note here that this methodology has some limitations on the maximum quantity of the bids, because we must not have a large deviation between the initial point and the final operating point. So we will see here briefly how the market operates. So the market instance is triggered by market participants. They submit their bids in the order book. And as we said, also the market operator and the DSO participate in the market. So the market operator is the one who operates the market and checks for the feasibility of the trades. But in order to check the network feasibility, some data from the DSO are required. These are data that are calculated every time a new forecast is made by the DSO, and are mainly the sensitivities and the margins from the operational constraints. So a market participant submits the order in the order book. The orders are ordered in terms of their price and then in terms of their timestamp, and then their feasibility is evaluated. If trade is feasible, then we have an update in the order book. This means that the traded volumes exit the order book, and if we have a partial matching of bids, then the remaining volumes remain in the order book. And of course, the market schedule is updated, and this information is forwarded to the DSO in order to rerun the AC power flow and the new sensitivities. So, yes, how we calculate these sensitivities. We have both sensitivities of nodal voltage magnitude with respect to the active power injections. This is easy to calculate. We calculate it from the inverse Jacobian matrix, and we use this part of the matrix, as we have only active power in our market. And for the sensitivities of the line apparent power with respect to the active nodal power injections, we calculate this in two steps. The first step is to calculate the sensitivities of the line apparent flow with respect to the changes in the voltage magnitude and angles. And we already know the sensitivities of the voltage magnitude and angles with respect to the changes in the active nodal power injection. So we can then calculate the sensitivities of the line apparent flow with respect to the active nodal power injections. And we use here this part of the matrix. So why we calculate these sensitivities in order to see the impact of the trade in the system, both in the line apparent flow and in the voltage. So for the line apparent flow, this change is affected by both the buy order and the sell order. And how much is this effect? We calculate it by the sensitivities. And because the trade will be concluded in the single quantity, then the change in the apparent power is actually dependent on the difference between the AC sensitivities of the buy and the sell order. So if this difference is negative, then this means that the apparent power flow of the line decreases. So this trade will help in solving the violation. And this is actually the first criteria for the network feasibility check. Now, the second criteria is not to cause any problems in other parts of the network. So we need to respect this limit, the thermal limit. So this causes a constraint in the maximum quantity that is possible to be traded. And this is also dependent on the sensitivity factor. And we can also find the minimum quantity. This is not crucial for the feasibility of the market. It's just an indication if we will have a full resolution of our problem or a partial resolution. So again, we also need to respect the voltage limit. So again, the quantity of the trade is limited by the voltage limitation. And we can see a simple example here. We have a simple network of 5 buses and 5 lines, and we see here the thermal limits of the lines and also the bus voltage limits. And we can observe that this line, line 1, is congested. So we will try to solve this congestion. So we will calculate, we consider 2 orders, a buy order in bus 2 and a sell order in bus 2. And yes, we calculate the sensitivities. These are the sensitivities actually of the order of bus 2, the impact of the order to all the lines, and this is the impact of the order of order 3 in bus 3 to all the lines of the system. And this one is for both the directions of the line. And in a similar way, we calculate the sensitivities of the orders to the voltage magnitudes. So we see here the difference between these sensitivities, and we observe that in line 1, which is the congested line, the sensitivity is negative, so this means that our trade will solve the congestion. But we observe that in line 2, the sensitivity is positive. This means that our trade will possibly cause a congestion in line 3. So we need to limit the quantity of the trade in order not to cause this congestion in line 3. And similar, we need to respect the bus voltage limits. So here we see the maximum quantity that can be traded. This is 6.5. If we have, for example, a trade of 10 megawatts, then we will have a partial match of the bid. This will be cleared, for example, not 10, but 6.5 megawatts. But now we have 2 megawatts, so the trade can be fully cleared. And also we see that our trade will fully solve the congestion. So let's check if this is true. Yes. So this is the AC power flow after the trade, and we see here that our congestion has been fully solved. So here we also we only deal with line congestions. An idea will be to further investigate other type of violations, like, for example, voltage violations or deviations in the TSO-DSO schedule. And also in this case, we need to find a way to evaluate the feasibility of the trades, because in this case, maybe the trades will be conflicting between each other. We need also to calculate this effect of sensitivities to the traded quantities and also consider the effect of grid losses in our system. So thank you very much.
Okay. Thanks for our speaker, and we are ahead of time, so I think we have time for questions. Yeah. Please.
Hello, Miad Reza Shafiqa from University of Vasa, Finland. I have one question, very interesting presentation, but could you please elaborate more about the coordination between the market operator and your proposed local flexibility market operator? Because I didn't see in the flow chart, it was just input from the DSO. And
yes, the market operator receives some data from the DSO. These are the sensitivities. And the distance of, let's say, the voltages and the lines, or line apparent flows, from the limits of the operational limits.
Okay, so DSO here is a kind of just linking between the TSO needs and other market operator needs with your proposed market operator?
We have one market operator.
So the local flexibility market operator and the market operator are the same?
Yes,
okay.
Yes. The market operator, we mean the local flexible market operator.
I think we can discuss after.
Okay.
Thank you.
Do you have more questions? Okay, I guess now thanks our speaker, and we'll proceed to the Okay. Yeah. I'd like to welcome our second speaker, Anna Schumacher, talking about water pump flexibility.
All right, hi, I'm Anna Stumacher, and this work is in collaboration with Johanna Matthew. So for my past research, I've been looking at leveraging the coupling between the water distribution network and the power distribution network. And so this kind of follows along those lines. And in this talk, I'll discuss how we can incorporate uncertainty in a way that remains computationally tractable, but not overly conservative. So to provide some background on this work, there is this growing body of research that looks at leveraging water supply pumps in the drinking water distribution network as flexible loads. So this is due to the fact that water distribution networks have this spatial and temporal flexibility. So pumps in the water distribution network are loads at different locations in the power distribution network, as well as there's these water storage tanks where we can store and supply water and still meet consumers' demands for treated drinking water without the pumps necessarily being running. So because of this, we're able to provide services to the grid, and in this talk, we focus on this from the perspective of providing voltage support to the power distribution network. So there are some challenges associated with this problem. The first is that we're incorporating both networks models that have non-convex constraints, as well as we're incorporating uncertainty, and so this ends up making the problem pretty complicated. So there are a number of ways that we can handle uncertainty in this coupled power-water problem. So I'll talk about a couple and their pros and cons. So first, we have a chance-constrained method where we use the scenario approach. And so if we apply some approximations and relaxations to this problem, we can use the scenario approach for convex problems. And so a benefit of this is that it's very easy to apply. So with the scenario approach, we just need to incorporate a certain number of uncertainty realizations and then solve the problem robustly. However, this can end up being pretty time and memory intensive, especially for larger problems. We have a larger set of uncertainty, and so it can be taxing to include all of this in there. Also, the scenario approach is very characteristically conservative. Another route to go, oops, sorry, there's a mosquito. Another route to go is a robust approach, and so if we apply some power flow approximations and leverage a very useful monotonicity property for the water distribution network, we can get a deterministic problem. And so a benefit of this is that this is quick to solve. However, since we're considering all the uncertainty, it can also be pretty conservative. So given this, we are interested in an approach that is computationally tractable and less conservative. And our goal is to optimize and control the water pumps in the water distribution network to provide voltage support given power demand uncertainty. And so we do this by managing the uncertainty differently for both systems. So in particular, we have a chance-constrained formulation to manage the power demand uncertainty in the power distribution network, and a probabilistically robust formulation to handle the impact of the power distribution network uncertainty on the water distribution network. And so this formulation kind of comes about naturally in that we have tools for the water distribution network that we can apply, but that don't necessarily apply to the power network. So I'll first talk about this in a very kind of generic form, and then I'll get into some details. So in this problem, our uncertainty is the nodal power demand forecast error, delta rho, at every bus k, phase v, and time t. In this problem, we want to solve for the scheduled pump power consumption, as well as kind of like this real-time pump control policy that adjusts the pump power consumption based off of uncertainty realizations. And so for this, we have like voltage support control policy parameters, as well as the required capacity we would need to provide this kind of service. So the cost in this problem, we want to minimize the scheduled pump energy consumption, which is this first term here. And then we also have a cost associated with providing this real-time voltage support capacity. And so we define this by looking at the total amount of real-time capacity that we would need. And as I mentioned on the previous slide, we are handling these power flow and water flow constraints somewhat differently. So I'll first talk about the chance-constrained power flow. So in this model, we use LIN3 disk flow, which is a three-phase unbalanced linear power flow model. We also employ an affine pump power control policy. So we're adjusting the real-time pump power consumption based off of the uncertainty realization. So in this problem, we're solving for the scheduled pump power consumption as well as this control policy parameter matrix. So in this problem, we want to ensure that the voltages at each bus and phase are within these safe operating limits. And given our model, we can reformulate these constraints as a function of the voltage magnitude squared, which is based off of the decision variables and the uncertainty. And so we apply individual chance constraints to this problem. And so we want to ensure that these voltage limits hold for a high probability at every bus phase and time period. And so given this formulation, we can analytically reformulate these given some known distribution, and we'll get second order cone constraints. So before I go on to the probabilistically robust water flow constraints, I wanted to provide some background on the water distribution network. So in the water distribution network, we want to ensure that the hydraulic head, the tank levels, and the pump flow rates are within these safe operating conditions. Additionally, we have these water flow constraints that are non-convex, and this is due to the pump performance curves as well as the head loss along the pipes. So in this formulation, we'll be utilizing the monotonicity properties, which are really helpful in dissipative flow networks. And so they apply to the water distribution network, given some assumptions on the operational and configuration choices. And so effectively, we can say with these properties that as the supply pump power increases, we see that the hydraulic head decreases and the tank level increases. So to illustrate how this is very useful in our water flow constraints, here we have a robust example. So gamma here is the set of water flow constraints. And so our pump power is a function of the uncertainty. And so if we want to ensure that the water flow constraints are feasible for all uncertainty realizations, we can equivalently look at the extreme pump power set points. And if those are feasible, then all intermediate points will also be feasible. So this brings us to the probabilistically robust water flow. And in this case, we want to analytically solve for a bounded set of pump power consumption values given the uncertainty. And this set would include a user-specified probability density. So we have these probabilistic statements on the right, and we're effectively saying we want the real-time pump adjustments, given our control policy, to be within these maximum increase and decrease in pump power consumption. So given this set, we want the water flow constraints to be feasible for all points. And so this is where we apply the monotonicity properties to look at these extreme operating conditions. And if those are feasible, we can ensure feasibility for all points within the set. And again, with these probabilistic constraints, we can analytically reformulate them given a known distribution. So this brings us to the case study. So in the case study, we look at this coupled power and water distribution network, and the dashed line just indicates where the pump is a load in the power distribution network. So in this problem, we consider two different uncertainty distributions, a multivariate normal distribution and a multivariate student t. So we differentiate here between the actual distribution and the assumed distribution. So in our formulation, we choose that the power demand forecast error, and we assume that it's a multivariate normal. And so our assumed distribution is fitted from 500 random samples of the actual distribution. So it should be noted that we could also reformulate these chance constraints, assuming it's a student t distribution, but we want to look at this case when the assumed and actual distribution are not the same. So we compare our probabilistic approach with a robust approach that also utilizes the monotonicity properties, as well as a deterministic approach where we assume we have no uncertainty and just perfect knowledge, and that'll just be the benchmark between these two approaches. And lastly, while it's not needed to reformulate this problem as a deterministic problem, we apply some approximations to the water flow constraints to make the problem fully convex. So here we first compare the solutions of our new probabilistic approach with the robust approach. And so for the probabilistic approach, we have varying individual violation levels. And so in the table, we show the solver time, the total cost as a % increase from the deterministic solution, as well as the average voltage support capacity over the scheduling horizon. So the first thing to note is that the probabilistic solutions and the robust solutions have a relatively comparable solver time. And I guess to further emphasize this, if we solve this with the chance constrained method using the scenario approach on this computer, we ran into memory issues and were not able to solve it. So if we look at the probabilistic solutions, we can see that as the violation level decreases, we see an increase in voltage support capacity as well as cost, which intuitively makes sense as we're now incorporating more uncertainty that needs to be feasible within the problem. And then lastly, as we look at the probabilistic solutions and the robust, we see that this probabilistic approach is less conservative than the robust approach, and so we're also more likely to find an answer. So this just is a figure to illustrate this. This is one example of the probabilistic solution with the robust solution. So the blue solid line is the probabilistic schedule of the pump. The green dashed line is the robust schedule. And then those blue and green bands are the amount of voltage support capacity we would need. So in this case, we want to minimize the amount of voltage support capacity since there's a cost with this real-time shifting of pumps. And so we can see kind of visually from this that the probabilistic is less conservative than the robust problem. So last, we compare the approach's performance when the uncertainty information is well known versus when it's not well known. So in this table here, we test the solutions generated from the assumed distribution, and we look at the empirical violation probability when the actual distribution is either normal, which is expected, or it's a student t distribution, which is not expected. And so we can see here that when the distribution is not expected, we can see that the violation probability performs worse. And so this, I guess, is to be expected since the student t distribution will have heavier tills, and so it'll have more extreme pump power deviations or power demand deviations than we would expect, and so the pump cannot encounter that or expect that. I guess, but either way, we see that the probabilistic solutions have a better empirical violation probability than the deterministic, as well as in this problem, the robust was not able to solve, and it ended up being infeasible. I guess just in one additional thing is we can see some benefits to the coupled system as a whole in this case. So just to summarize, we formulated a computationally tractable, uncertainty-aware, coupled power-water problem where we're including chance-constrained power constraints as well as probabilistically robust water constraints. And we see that it's less conservative while still remaining computationally tractable. However, we see that it may not perform that well when the uncertainty information is not well known. So this concludes my talk, and the contact information is below.
Okay, thanks our speaker. And one question. I see the hand. Yeah. No, yeah, please. Yeah.
Hi again, Miad Reza Shafiqa from University of Vasa, Finland. I have one question about your new type of flexible load. From your simulation, I thought that you simulated in hourly, but I'm not sure that this flexible load can provide some flexibility for the system in a shorter time or not, because we sometimes need some flexibility for milliseconds for the system, but I'm not sure that this flexible is how much your flexible load is fast.
Yeah, so that's a great point. So I guess in this problem, we're looking at it from the 1 hour time point. So we have these quasi-steady state power flow and water flow constraints. But the water distribution networks in general usually have a SCADA system, and they are capable of fast operational control. And I guess while we didn't necessarily explicitly look at this in the problem, with the monotonicity properties, we could ensure like feasibility at shorter timescales within the hour, as long as we're looking at the extreme like pump set points.
I'm asking this because I'm looking for the application of this new flexible load for providing different flexibility for the system. For example, for congestion management, I think it can be used. But for example, for frequency control or voltage control, may not. I'm not sure. That's why I'm...
Yes, so I think from, I guess, my perspective in the problem is that we have this total range of capacity for each hour, and then we can act on it in shorter timescales.
Okay, thank you.
So I'll stand up for 1 minute left.
Sorry?
I'll stand up.
Oh, yeah, okay. But there's a time on the presentation as well.
Yeah. Okay, welcome our next speaker, Thomas Offergeld. We'll talk about privacy and flexibility.
Okay, thank you very much for the introduction. As Bolin said, I'm going to talk about our work on aggregation performance for flexibility coordination schemes. And for my motivation, I will start by decomposing the title of our work into its 3 parts. So starting with flexibility first, obviously flexibilization will be a main cornerstone of the transformation of the energy system with changing generation and consumption landscape. Flexibilization will be used for balancing supply and demand, relieving grid congestions, and also economic optimization. And flexibility coordination schemes can be used to coordinate these use cases, but also coordinate between different flexibility providers. 2 approaches that we've looked at in our work are what we call a monolithic flexibility coordination, which is basically just a centralized way of coordinating different flexibilities seen in the top right, and also hierarchical flexibility coordination, where we look at a way to use intermediate aggregators to coordinate flexibility locally, and then use unused flexibility for the whole system level. And this is just a brief illustration of this. So here we have a two-level coordination with one level of intermediate aggregators and one top-level aggregator. But of course, looking at the power system with voltage levels and so on, there could be multiple levels as well. And the next point that I want to get into is the topic of privacy considerations. Obviously, with the hierarchical flexibility coordination, we have the advantage that information is only shared locally. We've heard yesterday that information is very important as well to learn about the system, for example, for adversary reasons. So here we have the advantage that we can control who has the information about individual flexibilities. In the monolithic approach, all the information is collected at one point, and in the hierarchical approach, it is collected in different levels of the system and then abstracted away and provided further up. This is very important because many of the flexibilities that we have to consider in the future will not lie within the hands of, for example, grid operators, but also utilities or prosumers. And the final point that I want to make are issues of aggregation performance. So obviously, as I just said, the hierarchical flexibility coordination will give us the opportunity to hide some information, but this will also then have the issue that not all information is available for decision making at all levels. So we'll have to also look at what impact that has on the coordination of the flexibility, how well the flexibility is used. And from that, we derived that we would like to develop a framework for the evaluation and comparison of different flexibility coordination schemes and aggregation methods. With that, we derived 4 research questions that we wanted to answer in our paper. First of which is how the flexibility potentials, especially from energy storage systems, can be aggregated to be considered in power system simulation. Which metrics can be used to describe the loss of accuracy during aggregation that I just mentioned, and how the properties of the flexibility providing units or flexibilities affect this aggregation performance. And finally, we wanted to look at if there are simple guidelines for this aggregation that can be used to reduce the impact of the aggregation performance. Next, I would like to look at modeling distributed flexibility potentials. Now, the details of this are in the paper, obviously. I just wanted to highlight the most important parts. The flexibility potentials that we are looking at are especially energy storage systems. We are modeling them in a time-discrete mathematical model where we describe the flexibility as the deviation from the normal behavior of the system. We are using linear models, but these models are generally exchangeable for this. Modeling flexibility potentials across a number of time steps will require us to look at time coupling behavior. So for example, for generators, common time coupling behavior or constraints are ramping limits, where the set points of active power, for example, are limited to within a range of the previous set points. For the energy storage systems, obviously the continuity of the state of charge is something that we look at, and keeping the state of charge to within its allowed band. So the linear models of the energy storage systems that we are looking at comprise active power set points. So we are not looking at reactive power flexibility, just active power, and also the temporarily linked state of charge variables that we have to keep track of. Next, I'll go into the issue of aggregation. So how are we aggregating these models, and what evaluation metrics are we looking at? First of which, the aggregation. So just a simple example, considering a system with, for example, 2 energy storage systems. We are aggregating those together into a virtual energy storage system. As I said before, this is something that could be then stacked in an entire system, and the aggregation we follow is quite simple here. So we sum up the active power flexibility and also sum up the weighted sum of the state of charge, which is basically just saying that we are summing up the energy or the capacity of the systems and the current energy. And in terms of evaluation metrics, we've looked at two different ones. The first one, which we call aggregation error, is a way to measure basically how the hierarchical flexibility coordination will overestimate the flexibility potential by looking at a difference, which we will see later, between the requested flexibility and the flexibility that's actually provided. And the second metric that we introduced is the aggregation efficiency, which is a comparison of the hierarchical and decentralized flexibility coordination scheme. All right, then I'll just go over the simulation approach briefly. So we are, as I said, looking to compare the hierarchical flexibility coordination with the centralized flexibility coordination. And for this simulation, we go into this with some scenario parameters that we'll look at later. So we have generation and demand time series that we can't control. And then we have parameters for our flexibilities that make up the scenario that we are looking at. And then thirdly, aggregation modes, which I'll show in a minute. And then we basically simulate the two approaches. So looking at this monolithic flexibility coordination, we will determine the flexibility potential at this coordinator in this coordination scheme. And then from this flexibility potential, determine a flexibility dispatch that we want to dispatch then to all the flexible units in the system. And for the hierarchical approach, obviously, we have to do this in a bottom-up fashion. So we are starting at the lowest level, at the lowest aggregation level, again, determining the flexibility potentials, abstracting them for the next higher level until we reach the top-level aggregator. And just as in the centralized approach, then we will generate a flexibility dispatch and then dispatch this flexibility in a top-down fashion. And then this leaves us with two flexibility dispatches that are described as time series for each flexibility that we can then compare in terms of the metrics we just established. And one point on the flexibility dispatch, this is something that in this paper we generated synthetically. So when we have flexibility potential, we look at one flexibility demand timeline or time series and dispatch this flexibility demand within this system. Okay, before I get to some exemplary results, I'll just outline the investigation setup for them. So here we are looking at a system that is just made up of 4 individual flexibilities, so 4 energy storage systems. We are not considering any grid constraints between those systems. So within the system, we assume to be constraint-free, but we could add constraints as well by limiting the flexibility potentials. And we're looking at 2 high-power systems and 2 high-energy systems, because this will allow us to look into different aggregation modes, what we've called them, that are shown down here in the table. So we have one heterogeneous aggregation mode where we take different or dissimilar flexibilities and aggregate them together on this lower level. And then we have one homogeneous aggregation mode where we match the flexibilities that we have and aggregate them together. And in our investigations, we are looking at a time frame of 1 day, simulating in 15-minute time steps. We are not looking at ramping behavior because for energy storage systems on that time scale it's not relevant. And for this, we've set charging, discharging efficiencies to 1, but this is a parameter of course as well. The root level aggregator seen up here, of course, needs a goal to generate a flexibility dispatch. And here we are just peak shaving an active power profile to generate this dispatch and actually have a use for the flexibility that we want to look at. Now for some exemplary results. So this is first the heterogeneous aggregation. In the light blue color, we see the active power profile that we actually want to peak shave. That is seen by the root level aggregator. And then we have 3 different lines. So the dark blue is the flexibility coordination or the result of the flexibility coordination by the centralized flexibility coordinator, which we can see achieves a reduction of the active power at the root level aggregator. And then the 2 other lines, so the red one is the planned use of flexibility in the hierarchical flexibility coordination scheme, and the gray one is the realized flexibility use in the hierarchical flexibility coordination scheme. Obviously, there's a mismatch. This is due to the information loss that I just mentioned. So here, grouping together dissimilar energy storage systems leads to an overestimation of the flexibility potential seen by the red line, and then the delivery of the flexibility is suboptimal. Going into the second aggregation mode, the homogeneous aggregation mode, we can see that here the red line, the dark blue line, and the gray line actually are superimposed. So here we have an aggregation that is lossless in terms of the information loss. So there's no difference between the centralized coordination and the hierarchical coordination in terms of end result. So taking away from that is that the impact of this information loss in aggregation can be reduced by combining similar flexibilities in this system. So for energy storage systems, this seems to be the case here. And one further aggregation mode that we wanted to investigate was actually trying to find out which parameter of the energy storage systems is responsible for this mismatch. So here we're looking at a system where we've kept this heterogeneous aggregation. However, we are doing a homogeneous scenario in terms of the power to energy ratio. So the maximum power that each storage system can provide, the ratio to the capacity is in this case the same, but there's one large and one small storage system in each of these two subsystems. And what we can see here is that the same as in the homogeneous aggregation, that the aggregation result is again the same for the centralized and hierarchical coordination. Therefore, it seems that especially this ratio of power to energy or power to capacity is responsible for a mismatch between this hierarchical and centralized coordination. And before I finish up, two more questions that we want to answer. So what's the quantitative impact of this varying power to energy ratio for energy storage systems? And the second, are the proposed metrics actually uniform across the flexibility range because we are looking at only one flexibility dispatch? Or are they actually a function of the flexibility dispatch and we would have to look at many more flexibility demand time series? So the result of that is that we've, in this smaller subsystem, varied the capacity of the energy storage systems. We've maintained the overall capacity and power, but altered the distribution of the capacity. We see that the aggregation error starts to significantly increase looking at the blue line when one storage system makes up about 75% of the total capacity. When we start to also introduce an imbalance to the power of the two systems, this is of course shifted. And then finally, we've seen that different flexibility demand profiles, which we had generated, also lead to different aggregation errors. So obviously there's some work left to be done to also look at how we can evaluate these aggregation errors over the entire flexibility demand domain. And with that, I think I covered everything I wanted to say. Just a brief outlook. So what I just said, looking at the entire flexibility domain, but also maybe include grid constraints for this subsystem, introduce further aggregation and coordination schemes, and maybe do a validation of the approach with some hardware as well. And with that, I'm done with my presentation. Thank you very much for your attention.
Okay, that's our speaker. I see Shmuel have a question.
Hi, Shmuel Oren, UC Berkeley. I haven't heard you talk at all address the issue of private information and information asymmetry between the aggregator and the storage owner. Like, how do you address, how what kind of economic incentive does the aggregator provide to induce truthful revelation, let's say, of state of charge or other relevant parameters? And how do you avoid adverse selection and moral hazard on the part of the asset owners?
So I think this is a question that might be answered by different aggregation schemes. The one we looked at basically describes what information we aggregate in which way, and this aggregated information is then parameters for this virtual model that we use to provide to the aggregator. And I think in terms of the value of this information, that has to be seen, what the value actually is. We showed that there's...
You're dismissing 50 years of economic research on mechanism design, information asymmetry, that looked exactly at those problems, that you have an agent, you have principals, and you're trying to collect private information from the owner of the assets. I mean, that's not something that's publicly available. So you optimize over something that is invisible to the aggregator.
Yeah, but I mean, when flexibilities want to participate in a flexibility coordination, of course, there has to be a monetary incentive, but then this flexibility coordination will, of course, require also an exchange of information. But that the exchange of information is probably not the same everywhere. It can range from very limited information to a lot of information. And if a lot of information is worth a lot, then, of course, that would be something that had to be incentivized by the aggregator for the participants.
But that's not part of your simulation.
No, it's not. That's true, yeah. Okay.
Yes, thanks our speaker again. Okay, and welcome to our next speaker, Elena Richeva, who will talk about flexibility in a carbon-neutral power system.
Hi, everyone. So my name is Elena, and I just want to acknowledge my co-authors, Jared Garrison, and my supervisors, Gabriela Hook and Christian Schaffner at ETH Zurich. So the topic of the talk today is the value of flexibility in a carbon-neutral power system. So we are all here today and every day because we're trying to answer different questions. And they're always in the context of the energy transition, be it around the globe or in Switzerland where I live. And here I just put two of the main questions that I've been thinking about lately. And one of them is, what could be the future generation mix? And also, what kind of flexibility can we use to accommodate for that? And the more I think about these problems, the more I realize that there's no single best solution. And also the approaches that exist in literature, they're not applicable like to every system. So there's no one size fits all. And today, during the talk of Professor Lopez in the morning, I, for the first time, saw a guess at how the power system could look like for the case of the Iberian Peninsula. And that made me very happy because actually people do use best guesses when they, as a starting point, when they do their research. And today my talk is about best guesses. So we need to start from somewhere. We don't have a crystal ball, but the best second thing that we have is sort of planning studies. And so for the ones of you that are not super related to the field of expansion planning, this is a model. We are solving an optimization where we co-optimize generation, operational decisions, and investment decisions. And I just decided to kind of summarize for you the state of the art relating to energy transitions. And then we have a few focal points. So people are interested in flexible loads, in operational detail, uncertainty, solution techniques. And I kind of put in the back the real power system part. Because very often you have these model test systems, very few representative periods that are not really covering the whole picture. And in literature, people are trying to address maybe 1, 2 to 3 of these focal points, but today we're going to try to do a bit more, and we're going to focus on the part of the real power system. And in this context, the objectives is to model different sorts of flexibility, so dispatchable generation, load shifting, and then the ability to import and export, and then see how these impact investment and operational decisions for a carbon-neutral future power system. So this is a brief outline of the talk. I'm going to go really not in so much detail into the problem formulation. Then we're going to look at the test system, some results, in conclusion, and outlook. So problem formulation. As part of my work, I developed a generation expansion planning formulation. I named it, very attached to it. It's called CENTIV. It stands for Centralized Investment Planning. And it's a model, large-scale model. I linearized it recently, and we aim to co-optimize, as I told you, operational and investment decisions for a given year. So it's a static expansion planning problem. And it's a large-scale formulation, and it relies on a lot of input data. And this is kind of summarized here on the left. So we have operational parameters and weather time series that goes into the operational model where we tell our generators how to operate. We have the transmission system, our system demand that goes into a DCOPF power flow model. We have reserve requirements to cover some reserve margins and also investment constraints to decide on what generators to invest in. And all of these models kind of talk to each other through different constraints and different variables that we constrain with, again, the objective of minimizing operational and investment costs. And here I just want to make one statement, and that, in my opinion, generation operation, the utilization of grid, investments, and reserves, they're very intertwined, and they need to be co-optimized together. A bit on the grid model. So as standard in usually planning studies, because there are very large problems that we're trying to solve, we have a DCOPF formulation, we have our nodal balance, our demand, we have some line limits, and then what we do slightly differently in this paper is we kind of disaggregate the demand. We say, okay, we have a base demand, we have a heat pump demand, electric mobility demand, it can be also industry demand, hydrogen demand, and so on and so forth. And we introduce kind of simple ways to control these different types of demand. And just for electric mobility, here's an example. So in each hour, for each bus, we introduce a variable for shifting up and down. And this variable hourly is constrained by power. So there's a maximum power up and down. And it's during a day constrained with an energy constraint. And we can shift, we should shift up and down equally. So with this sort of like very basic way to control demand, we plug it in the formulation, we put all our control variables. Wait, can you see the, yeah, up there, and we solve now our large-scale linear problem. And again, another statement that I want to make is that it's important to differentiate between different types of flexibility providers and different load types, because it can help unlock hidden potentials, and it's also another step towards going to power to X and sector coupling things in generation expansion planning, which is not really researched so much so far. And so a bit about the test system, since I told you that it's going to be a real test system. We use a reduced version of the Central European power system for 2040, and that means we simulate Switzerland here with full detail, and we aggregate the 4 surrounding countries, so Germany, France, Italy, and Austria. But then the question is, what do we do beyond then? You see Switzerland, it's small, and it's right in the middle of everything, so we need to find a way to kind of understand our boundary conditions really well. So in order to do that, we use a mixture of projections from the 10-year network development plan of ENTSO-E, but also we use simulation results for another module. It's called Calliope, and it's work of our colleagues from University of Delft and previously ETH. And so they give us results for the generation and for like the investment mix in the surrounding countries beyond our 5 countries, and they give us the boundary conditions to be able to carry out our simulations for a version of a carbon-neutral power system. So, yeah, if you're interested, this is their work. So we simulate a couple of different sets of scenarios to understand the value of flexibility. So our first scenario is the baseline, and there we have 4 different simulations that we run that I describe here. And we set a 25 terawatt-hour target that just comes from national target of Switzerland that they want to have for 2040. So we have no gas candidate units and no shifting. No gas candidates units and shifting, gas candidates units, no shifting, and gas candidates units shifting. And then for the second set of scenarios, we use the baseline, but we say, okay, let's reduce the import-export like capacities to quite significantly, 70%, and it's actually a legitimate concern of Switzerland right now, but I'm not going to go into details. And we're going to designate these scenarios with a R in bracket. And in the end, I'm going to show you a sensitivity analysis. So, baseline scenario, what do we see when we run the simulations? Here are the results in terms of the investment, the objective function value, and also the load shedding for Switzerland and outside of Switzerland. And what we see is that as we get to the point of with load shifting and with flexibility, we kind of get the best objective function value. We get the best in terms of we have the least PV investment. And by the way, in all simulations, the PV target was covered, but that was it. Nothing was built over it. So what this means is that if we have flexibility, we can accommodate for renewables, but we don't have to overbuild them. So yeah. And again, as I said, the combination of having both load shifting and flexible generation gives us the best performance in terms of reduction of the objective function and also least load shedding. And because we simulate with hourly resolution, we can kind of look also really inside and understand what drives investments, what happens to the operation as well. And here you can see on the left, this is a production and consumption stack per technology type for 1 day in October. And this is a day that's characterized by a lot of load shedding. So here's the production, here's the consumption, and we compare the best scenario, so with gas, with shifting, to the kind of worst scenario that's no gas, no shifting. And what we can see is that both gas and shifting help us reduce the amount of load being shed there. Also, what we can see is that there's different operation in dams in off-peak hours. And then if we start looking into the operation of dams, you can see it here. It's the end-of-month storage levels of the Swiss dams. We see like two different sets of curves. So on the top is the curves that have the shifting, and on the bottom is the two scenarios that don't have shifting. So if we have shifting, we're able to keep a bit more water early in the year, and then we can use it later on. So that kind of also highlights the opportunities in being able to shift load. And now for the very bad scenario where we reduce the cross-border transfer capacities, we see a massive investment now in renewable generation in the scenarios where we are not allowed to invest in new gas units. The driver before was the renewable target. The driver now is the lack of capacity. And we also see a higher number, higher gigawatts of load being shed, gigawatt hours, of load being shed both domestically but also outside of Switzerland, which is very important. This means that there are implications of reduced cross-border capacity, not just in Switzerland, but in the outside, so in the other surrounding countries. And it's something that should be discussed in the region and should be taken account for. And so it's not just that the gas investments increased, it's that the operation of these units also changed. Before, gas was mostly used as peaker power plants, but now we can see in the operation part that gas is continuously being used during winter. And here again, you can see the stack for generation and consumption, but now we are plotting weekly resolution for the whole year, and we're comparing the with gas scenario with shifting and the no gas scenario with shifting. And so you can see what I described to you before. We have now a lot of PV. We are not able to have gas, so we need to compensate with something, and what we have as candidates is the PV. I mean, it doesn't mean that the system cannot cope, it's just a different realization. Also, we see a change in the operation of pumped hydro, where in both sets of scenarios, water is completely shifted from summer to winter. And so because I come from Bulgaria and we're very reliant on natural gas imports, I was kind of worried about the fact that in one of the scenarios, we have a significant amount of new gas that's being installed. And I asked myself, like, what happens if the price of gas increases, which I think is a valid concern. So I ran a couple of sensitivity studies to see what happens, really. And I ran it for the best realization of the reduced system scenario. So that was with gas, with shifting reduced system. And here you can see that even a 50% reduction, increase in the gas prices leads to about the same amount of PV that we saw in the scenario without gas. So our input assumptions are very important in terms of what we get as results, and our simulation is very sensitive to such assumptions. Also, something that kind of struck me and still strikes me is that, I mean, yeah, of course, we increased the price of gas, but our invested installed capacity decreased tenfold. So again, I just want to highlight the importance of running these sort of sensitivity studies to understand what drives actually your results. Now, a bit of a conclusion and outlook. So we used the generation expansion planning formulation for the year 2040 for a reduced Central European system. And then we saw that in this system, we need a lot of dispatchable capacity. We can do without it, but yeah, the best solution is to have both dispatchable capacity and load shifting, which kind of means that I want to emphasize the importance of having load shifting in your optimization problems and in your expansion planning studies. And again, bringing back to the introduction, well, there's no one size fits all. I mean, this is just one possible future, and it's subject to great uncertainty, as we saw in the sensitivity study with the gas prices. And about what's next, so this work has been done quite some time ago, and now we're looking at a combination of generation expansion planning with transmission expansion planning and risk-informed in terms of having cascade simulation and modeling cascades in the Swiss transmission system. We are really interested in being able to model uncertainty beyond scenarios and are still trying to find a tractable way to do that. And yeah, power to X is a very big thing, so we're going to try to do that as well. If you're interested in, I don't want to sound like a salesman, but we're developing a framework at ETH. So it's a framework of interfacing different types of models. So we have generation expansion planning for transmission distribution systems. We have cascading failure model. We have energy markets model. We're trying to understand if we can make them work together to make better decisions in future. So yeah, thank you.
That's our speaker. To a question. Misha.
Thank you very much. Very nice talk. I wanted to add one scenario, actually extending your scenario on gas. Not only if price will increase, another side effect is that load will increase because a lot of residential heating will go to electric. And that's probably, well, for some countries it may be even more important than increase, reshuffling of generation. Did you account for that or not?
So remember the part where I told you that we use simulation results from another model? So this model kind of simulates the whole Europe for a carbon neutral 2040 power system. And we include their assumptions on demand. And what they saw was exactly this, the consumption from electric heat pumps, electrification really went up. And I was surprised actually when I was looking at the input data because demand usually was not that high in our previous projected scenarios. But yeah, I mean, we do account for that through the work of our colleagues. But yeah, we did see an increase in heat pump demand.
Super, thank you.
Thank our speaker again. Okay, I will welcome our last speaker of the session, Bai Cui, who will talk about aggregation and flexibility.
Thank you, Bodo. Hello, everyone. My name is Bai Cui. I'm a researcher at Unreal. So today I'm going to talk about our recent work on enabling grid-aware market participation of aggregate flexibility resources. So this is a joint work with my colleagues at Unreal, Ahmed and Andre. So I guess I don't need too much motivation for this problem. We're in this flexibility session. We all know distribution systems are transitioning from passive grid elements to active virtual power plants. And especially with this new FERC Order 2222 regulatory barriers preventing DRs from participating in electricity markets are lifted, and people are thinking about ways to integrate distributed energy resources to the wholesale market. And this is an extension of our previous work on characterizing flexibility regions for a whole distribution system. So the question we're asking here is really, once we have this aggregate flexibility characterization of an entire distribution system, we know what is the potential, its power potential to supply to the wholesale market. How do we effectively integrate those resources into the wholesale market? So there are different approaches to tackle this problem and integrate DERs into the system. So the first one is, the current practice is for DERs to directly bid into the wholesale market, pretty much DERs or a set of DERs as aggregators, pretty much like a conventional power plants. So the obvious problem of this approach is that once you have massive amounts of DERs, the optimization problem really becomes very complicated. And since we have very stringent time requirements for solving this kind of problems, normally ISOs will have to resort to some kind of crude stopping criteria, and which will result in some random commitment of those small DER commitment. This brings about some fairness and equity problems among those DER awards. And also may lead to infeasible operations at the distribution system because those operational constraints at the distribution systems are not really taken into account. So the second approach, or the ideal approach, is to include the entire distribution system, including those DERs and also the network model, into the wholesale market. Of course, when we have a lot of distribution systems and a lot of DERs, this also results in a very large systems, and also it requires extensive communications between distribution system and transmission system, and also has some privacy issues about sharing those distribution system informations with the ISOs and so on, and also it's not compatible with the current market structure. So what we are looking at, or what we're working with, is imagine we have a distribution system and we can characterize this aggregate flexibility. So can we just offer those flexibility regions? So from the transmission system, from the wholesale market perspective, what the ISO really sees is this aggregate flexibility region, and so the goal of this work is to characterize this cost curve so that this aggregate flexibility region can be used in this wholesale market clearing problem. So before we dive into the details of this formulations of deriving this cost curves, here are some of the DERs models that we're using. So as we can see, many of those devices, they have time coupling constraints, for instance, energy storage units and HVAC systems. They're really time coupled, so this motivates us to develop not just the single time period, but multi-time period cost curves for those aggregate flexibility regions. We work with a linearized power flow model in distribution system, and we explicitly consider operational constraints. For instance, we consider voltage constraints here, and there's a linear relationship between the individual DER power output and also the power exchange between distribution system and transmission system, the P0 here. The compact model we'll be using is this the following model that captures the aggregate flexibility between the DER powers P and also the power exchange at PCC P0. So here's the problem statement. What we're trying to do is to design a multi-time step generation cost curve for this power exchange at the point of common coupling, such that for any power within this flexibility range, the total power described or prescribed by this multi-time step generation curve is going to cover the maximum payment to the customers by system aggregators for any feasible disaggregation strategies that the aggregators may have. So we recently are aware of another work that look at a similar problem where they describe, where they derive a similar multi-time step or a single time step energy generation curve for this VPP or this distribution system, where they just minimize this cost curve. Here we're really trying to argue that the reason we're trying to maximize this payment to customers is really trying to take into account the uncertainties of the distribution systems and also some random behaviors of those customers and DERs. So we really want to make sure that in the day-ahead market that they're not overcommitting or resulting in some infeasible commitment in a real-time operation. So the assumption we make is that we're assuming a flat buying and selling price for DERs. Of course, the selling price is going to be higher than the buying price, but we assume they're the same. They're flat, and we're not discussing a distribution market problem. So as we can see from this definition, it's not hard to see that this maximum payment manifold, or the at given P0 at given power exchange at PCC, this maximum payment manifold or this multi-time period actual cost curve is actually concave because of the linearity of this buying and selling price, and also because of the polyhedral structure of our flexibility region. So we're really trying to use two approaches. One is linear, one is quadratic, to upper bound this concave payment manifold. So the first approach we take is to consider a linear cost curve to upper bound this maximum payment, and we consider this set D plus to be our flexibility range. We're trying to make sure that we're trying to design a cost curve such that for any disaggregation strategies on the right hand side of that inequality constraint, our cost curve is going to upper bound that quantity. So for our objective function, what we're really trying to do is to make sure that our upper bound is set as tight as possible. So we're trying to minimize the volume under this linear cost curve. And that results in a linear function of our linear cost curve coefficient y and z. So the problem of this formulation is that we have a complicating orthogonality constraint. But luckily, from the nature of this problem, this constraint can actually be dropped. So we're left with a classical robust optimization problem with a linear robust optimization problem with a polyhedral uncertainty set. So this can be easily convexified and reformulated as a tractable formulation. So this y and z, this coefficient of the upper bound of the maximum payment curve, can really be efficiently captured. So the other approach we tried is we're trying to see whether we can characterize this upper envelope using quadratic cost curve. The problem with this curve, with this approach, is that we're not working with a convex quadratic cost curve, but a concave cost curve to better upper bound this concave maximum payment manifold. We can similarly describe this objective function as minimizing this volume under the cost curve ends up being proportional to a linear function of those coefficients of this quadratic cost curve, and we can formulate a similar optimization problem. But here, the constraint is really concave, and also this is a concave robust optimization problem, which is really hard to solve. So once we reformulate this constraint as the minimization problem, we see that it's a concave constraint. It's a concave QP. Luckily, for this concave QP, we know that this optimal points are obtained at the extreme points. So we can reformulate this problem as having all those constraints for all the extreme points for this flexibility set. But the problem is how to enforce those potential exponential number of constraints. So we leverage a constraint generation approach. In the first step, we just solve this master problem with a single extreme point, and then we check whether this problem is optimal or not by solving a sub-problem to add new extreme points to it, and we resolve this problem until optimal. So yeah, this results in an iterative approach, but nonetheless, we're just solving SDPs and also concave QP, which some commercial solvers like Ruby or C+ can be solved, can solve those types of problems to global optimality. We can also extend this approach to a single period cost curve. So the naive way would be just setting the time step to 1, just working with a scalar instead of vectors. However, we really would argue against this approach because this ignores those intertemporal constraints of those DERs, for instance, energy storage and also HVAC. So what we propose is the simple approach where we, retain this scalar cost function, this cost curve for a single time period, but on the right hand, we ensure that for any, DER disaggregation over entire time horizon, this cost curve is going to cover that. So we tested our two approaches on a real test feeder from Southern California Edison. First, it shows the constraint generation approach for this quadratic cost generation. Quadratic cost curve generation, we can see that it converges pretty fast. Around 20 iterations, it converges, and it drives this quadratic cost curve. And we also see that we also use some brute force method to calculate this actual maximum payment manifold, which turns out to be somewhat piecewise linear. We can see there's a breakpoint between the two pieces, and it confirms this is concave curve. And for this result, the linear cost curve and quadratic cost curves, they are pretty much similar to each other, but they're both computationally tractable. So as a summary, in this work, we are decoupling the transmission distribution system markers through aggregate flexibility characterization, and we propose a design of the virtual power plant cost curve. And for distribution system markets, which may not be operated in the most economic way, the cost curve should be designed with compensation, so to maximize over all the disaggregation strategies. And we also design multi-time step cost curve that considers resources with intertemporal constraints, and for both linear and quadratic cost curves, the corresponding optimization problems can be efficiently solved. So for some future directions, we're looking at alternative cost curve optimization, for instance, piecewise linear, as we can see from the simulation results. The actual curve under this linear approximation seems like to be piecewise linear, and we're thinking about more general distribution system market model beyond this flat price scheme. So yeah, that's all for my presentation. Thank you.
Okay, thanks our speaker. And one question before we go into the panel discussion. Please, quickly.
I just have a clarification question. Sakis Maliopoulos from Georgia Tech. I see that you consider the air conditioning, the time evolution of air conditioning. So how fast you run your time step?
So the time step is 1 hour. So
1 hour?
Yeah.
So does it make sense to use to use the dynamics of the air conditioning if you do 1 hour?
I mean, we're considering a day-ahead model with the energy storage. So and also for this HVAC system, I think I think the approach is quite general, and we can consider different timescales. But
Okay, so you cover generality basically, right?
Yeah.
Okay.
Okay. So now proceed to the panel discussion. I'll welcome all our speakers back to the stage, and I'll hand over to Daniel to host the discussion.
Well, I think we have had some excellent presentations, so I'm really looking forward to the discussion. So, as usual, line up behind the microphones, and who wants to ask the first question? Come on.
Yeah,
Flexibility is an important topic. Stephen.
So I will start. It's a question maybe for the panel, not specific or any speaker. So I think one of the papers yesterday touched upon this point where you have a bunch of DERs, say EVs and buildings and so on, and if you have an aggregator that communicate with the grid operator that worries about the operation of the grid. Now, the aggregator would know the DERs. So DERs, they have to do something. They are not only providing grid service, but they have to, say, charge the EVs, provide temperatures, and so on. So how do you do the communication between the state of the DERs and the state of the network in order to figure out the efficient decisions for the grid and also for DERs? So any comments on?
Big question. Who wants to tackle that first?
I'll try first. I think that's an important question because there's information at two different actors that needs to be brought together, or at least the relevant parts of that need to be brought together. So I think one approach would be to communicate schedules, and then the DSO, for example, or the grid operator in general could check if that's something that's feasible within the grid, or the other way around, that you could limit flexibilities preemptively by communicating like potential grid constraints, but you still end up with the challenge that you need to know about the location of flexibilities within the grid. I think this is something that is in the model where you have a separate aggregator and grid operator. There's something that needs to be solved by communication.
Just a quick point on that. So one way to think about this problem conceptually is that you have two parties, actually probably more than two, but one grid operator, one is, let's say, DERs, that try to optimize a certain optimization problem subject to a certain constraints. But each party knows a certain information. So for example, the aggregators may know the state of the, say, EV state of charge. That will allow you to make decisions, or allow each DER to make their control decisions. And the grid operator similarly, suppose they know the grid state, they have to make their decision, and both decisions somehow give you a cost that is global. So it's not very clear. Now, of course, if there's no constraint on communication, you can communicate all state information. Then, of course, you can solve the problem. Right? The practice is that you cannot, either for computational or communication complexity issues, or because of privacy issues. And therefore, how do you think about what is the right things to communicate, how often to communicate, and based on the local information that you can communicate, how to make the decisions? I guess just any comments from you guys, since you have been thinking about this problem for a long time.
I think I'll just quickly comment on that. I think one possibility would be to communicate, for example, sensitivities for critical grid elements. So the aggregators would know which elements are potentially critical and what effect the units they control would have in that. But maybe someone else wants to weigh in as well.
Anybody else wants to weigh in? No? Okay, so we'll go to the next question. Just the next question, please. Go ahead.
Good afternoon. My name is Enrique Vera from University of Waterloo. It's a question for Elena. At the end of your presentation, you mentioned that you've been looking into working with stochastic optimization without using scenarios. So I was just curious if you could expand on the idea of how to use that, what techniques you will plan to use, and what type of information you will need.
Yeah, sure. So you saw that from the scenarios that we ran, kind of PV stands out as the way to go in the future. So we plan to use different forecasts for PV and introduce that maybe in stochastic, some sort of a stochastic framework. The other option is to just do something like Monte Carlo, where we run thousands of realizations. We have different PV realizations, and then we establish the investments for that and kind of find bounds of what would be possible, like gas investments or investments in biomass and so forth. So it's a robust approach is, I don't think, gonna work for us very well. So it's gonna be either, scenario modeling like stochastic optimization or a Monte Carlo approach. Do you have any recommendations?
Well, just I work with stochastic optimization, and I've used different approach. I've used Brownian motion for my models to have kind of an optimal approach to generate the scenarios. So that's what I've done so far. So. Yeah, I was just curious what to do in case you don't want to go and start doing scenarios, because when you start doing that, you open up the door
it is horrible.
Yeah,
new door that.
Exactly, you open the door for like a lot of things, right? You want to create scenarios and then start reducing, or so that's what I was just curious. Thank you so much.
Misha?
Misha Chertkov, University of Arizona. Well, I kind of question / comment, I think to Anna and to Bei. Anna, I was very happy to hear about robust considerations used, which applies to gas. So in gas, that's actually a remarkable ability to reduce number. It allows us to reduce number of scenarios significantly, right? But Bei also mentioned, well, in some of your formulations, you have robust optimization, which is tractable, right, for power system. And now in power distribution, I'm guessing you are using clean dist flow, right? Okay. So now in power system, we know that this robust kind of theorem, which applies to gas, does not work in general. But in some situation, it may work. And it may work in a kind of, patchy way. So for some phase space, some part of a phase space, it may work. If you'll discover anything like that, it may lead to very significant improvement in how we handle robust optimization in a power system or in combination power and gas. So I wonder if, I guess first question to Anna, how exactly did you use robustness on the gas side, and if you try to proliferate it to power side? And I guess similar question to Bei.
So just to clarify, the question is how we, in the robust formulation, how we use that with the
how
water.
You took advantage of robustness of gas in your setting, which is coupled setting. I didn't quite. It's a kind of technical question. Yeah.
Right. So I guess though for water instead of gas. Is
I'm sorry. Yeah. So water. Yeah. So it applies. So robustness. Well, okay. Sorry, misspoke. Yeah.
I'd have to say I didn't look at that.
Originally, we introduced it for gas, but it's the same for water. Yeah. Sure. Mm-hmm.
I guess so. In the robust formulation we looked at, we also leveraged those monotonicity properties for the water side, and so that we had to. Oh, is this better? Oh, okay. Yes. So for the robust formulation with the water constraints, we also leveraged those monotonicity properties. So we looked at just the extreme points, since we were considering just the impact of the uncertainty from the power network, and that just directly translated through to the pump power consumptions, since we were using these real-time control policies to update the water distribution network operation.
But on the power side, you still went through stochastic, well, how you handle your chance constraint in the power?
The robust constraints in the power, yeah, so we use some linearizations first to reformulate.
So.
Yeah, Misha, can you repeat your question? So for
if you see any opportunities in kind of other technical ideas which will help us to resolve robust optimizations in the power distribution specifically, through taking advantage of some properties of like monotonicity, possible monotonicity.
Yeah, I think for distribution system, especially radio distribution systems, there are some nice monotonicity properties. I think monotonicity is really important for robust optimization problems because you can characterize upper and lower bounds of certain variations, and also find that different uncertainty sets can have a huge impact on tractability of different robust optimization problems. So even maybe we're dealing with the same power flow equations, but with different characterizations of the uncertainty sets, for instance, polyhedral or some other ellipsoidal that will impact the tractability of the optimization formulations. But I would definitely think for transmission, for distribution systems, the radiality offers a lot of monotonicity, and it can be helpful for formulating robust optimizations.
But you didn't use in your current work what you presented. You didn't use it.
No, because I'm using a linearized power flow model, which is already not too hard to deal with. So, but I think with a general nonlinear power flow equations, distribution system may also be able to have tractable reformulations.
Next question, please.
Hi, I have two questions. Mohammed Aoudallah from McGill University. So the first question is for Anna. The same point, I think you model the uncertainties. You have two uncertainties, right? One using chance constraint and the other one using the robust optimization. Why you picked, for the power flow, why you picked chance constraint? I think you picked chance constraint for the power flow, right? And for the other one, you picked robust optimization. Why you made this assumption and why is not the opposite?
Right, so I guess, yeah, so chance constraints for the power flow, but it was probabilistically robust for the water, and so we still have the same uncertainty that we're considering. We're just getting a bounded set of what those pump power values could be for the water. And I guess it ended up in that kind of formulation, since there are these, as we mentioned about the monotonicity, there's these tools that work really well for the water distribution network, but they don't translate over to the power network. So I guess both formulations, though, have this kind of probabilistic sense to it, and so we do have this sense of, I guess, for the water distribution network, we wanted to operate with high probability, so some of the limits are maybe a little bit more soft. If it's okay if the pressure changes outside of the limits. And then for the power constraints, we also had that chance constraint probabilistic formulation, so that there may be other network components that would also be dealing with the voltage violations. Does that answer your question?
Yeah, that's okay. Thank you. And the second question is for Elena. I think you talking about the generation expansion planning, and you have added some sort of flexibility from the loads, the shifting loads, right? Yeah. And with that, you achieved kind of savings in terms of operation, in terms of investment costs.
Yeah.
Yeah, but generally speaking, if you are making this kind of assumptions in terms of generation expansion planning, Is that a valid assumption? Because I would say in operation, that's fine. You have the units, and if you're gonna save some costs, that's fine. But for the generation, you have to be as robust as possible with the worst case scenario. That's how I'm thinking about the generation expansion planning and transmission planning too. But if you have that flexibility, that's fine in terms of operation. But like I'm just questioning about the assumption itself in terms of the expansion planning.
You're completely right. That's why also when we were simulating the scenarios, you saw that the worst baseline is no gas, no shifting. So we should always have a benchmark to compare to, but it's kind of more, I would say, these sort of scenarios, like the wishful ones, are sort of like informative of also what would you, so if you have good control of your system, of your operation, you could save there. So it's kind of a thing that should, these sort of studies, they should be communicated with TSO, with people that are operating the grid, so that they have an idea, DSOs as well, because like the load shifting, this would come from the distribution system. So, I mean, yeah and no. So it's better to have everything and be able to compare and contrast and show opportunities. I mean, when you do planning anyway, you don't know, but I think in these sort of studies, it's always better to kind of cover the whole spectrum.
But you're totally right. But if in terms of operation, so if that problem was formulated as a bi-level problem, where you have the generation expansion planning at the higher level, and you have the operational constraint at the lower level. It's just a general question. You think that things will be different? You'll be more robust in that terms, or that's going to change the solution?
I think it's going to change the solution. Yeah.
Thank you.
Yeah.
Thanks.
Any other questions? Claudio.
Claudio Canizares, University of Waterloo. I was curious of whether you look at other techniques to approach your uncertainty analysis or simulation. We have worked quite a bit on a fine arithmetic, which has not this, it's an interval approach, somewhat similar to robust, that doesn't require linearizations, which are an issue. And I was wondering whether you have looked at any of those, and the possibility of using this type of approach. Are you familiar with the fine arithmetics on interval? Well, I recommend you take a look at that. It might be useful for your, your simulations. Thanks.
Maria.
Maria Illich from MIT. I was going to return to Steve Lowe's question, actually. I don't know if I understood it 100%, but you were asking how do you take into consideration internal constraints if DR wants to bid in and still meet its own risk preferences, its own physical constraints and stuff like that. So I think it's one of the very tricky questions when you put the market rules, because at least in the bulk power systems, people say, okay, you are doing market power if you bid something which is not just marginal cost of fuel or marginal value of the load, so you cannot internalize those. So this DIMOS, Dynamic Monitoring Decision Framework, that we have been proposing, and I will mention just in one slide when I talk about it, is I think it makes much more sense to internalize your own constraints, your own risk preferences when you make the bid, because you can do model predictive under uncertainties. You can be much more confident as a stakeholder that what you can do and at what value within which flexibility ranges that somebody was talking about, then the system operator. And then you just clear those, like reinforcement learning. We have talked with FERC, with Dick O'Neill about this many times, and I think that NREL, I just heard last week the presentation, they are just getting into that like you differentiate between interruptible load or the load that must be served in emergencies and so forth, and then you put some number to it. The value is $1,000 per megawatt hour if you are completely uninterrupted and so forth. I think before that question gets resolved, I think we are just sort of running in circles with anything but just marginal cost. I don't know if I understood your question right, but I think it is very, very key question because like Elena, you were talking about centralized planner, doing everything, doing operations better, and then trading investments. It assumes all the risks, all the uncertainties are either known or they are actually managed in centralized way. That is, I wanted to mention that maybe 5 years ago, Maria Pritza at CMU did, and I think Gabriela knows about this, did the interactive planning proposal in which you actually do this, take into account how well you operate when you invest into it, but the stakeholders have the right to say, you know, like for the next 5 years, load is going to need that much. And that comes in a distributed interactive way when you negotiate the planning. Otherwise, I mean, the question on the table is who takes risks and how do you value all these uncertainties? So is that what I understood, Steve?
Can I respond? Yeah, thank you very much. Yeah, I think that really is one key question, how to internalize whatever aggregation of DRs, what they need and what they can provide that what the grid needs. So that, I think, is one tricky piece. But I want to add maybe one more tricky piece, which is that for planning, and I think that with those kind of ideas can work, but if we think about operation, then things evolve, right? Both on the grid side and also on the DR side. And therefore, they need to communicate as well. And therefore, I feel there are a few issues. One is how do you internalize or basically you have a whole bunch of DRs that will provide certain flexibility at one node in a transmission network, which consists multiple nodes. So what is the aggregate flexibility of this thing in a way that is useful for the grid, but also in a way that is simple to communicate, simple to compute? The second issue is as the states on both sides evolves, how do you make that communication, again, in a way that is simple but useful for each side? And then how do you value that?
If I can just add one more question. I think another thing that confuses me in these markets is that does the bid have to be implementable, physically implementable? That is another thing, you know. You can bid something, it's virtual, and then... So there are all sorts of moving targets here about what are you clearing and who is doing what, I would say. And that is, you're talking about DRs, but the same questions in bulk power systems. Yeah.
Right. Elena, you want to comment?
I just want to comment, and I think you're completely right. And so what we also try to do is, in terms of, again, generation expansion planning, we had a paper a year ago with a colleague from Gabi's lab, but she already graduated. We tried to see if we can coordinate expansion planning for transmission distribution systems. And the communication in our case was, I mean, it's iterative, so I run, so the transmission system runs. It produces like the dispatch, and it also, as a result, it produces the duos on the like power balance. So you get some price signal. I mean, how good that price signal is, you know, this is another question. So, and then the distribution system gets this price signal, and they take a different perspective. So they take the perspective of the distribution system with the households, with the DSOs, with the large consumers. So they see these price signals and they say, okay, that's my price to purchase the power. I can either take that or I can build. I can build and then source it locally. And in some cases, I can even inject back to the grid. So yeah, we are working on such a formulation, but yeah.
Because if you don't do that, you don't give choice.
Exactly. And no, it's completely different objectives. I mean, the transmission system operator minimizes cost, but that's not what the The consumer does. Yeah.
So any other questions? In the back, please.
Hi, Rajkumar Palaniappan from the TU Dortmund University. We saw a lot of optimization with flexibilities. So have any of you tried to explain these systems to the system operators, and what is the feasibility that this could be actually put in practice?
Anybody dares answer that question?
I can try to tell you in the context of Switzerland. So we do have interaction, I would say, with the Swiss grid, so the transmission system operator of Switzerland. And from experience, what I can tell you right now that they're most interested in is not the central system, it's not what I do, but it's like the projection of where the distributed energies are going to be, so the distributed energy resources are going to be. For them, that's a very, very interesting thing to look at, because they look at these injections and they try to, because just in Switzerland, this is like most of the new power is going to come from the distributed energy resources, and they want to plan their power system having these in mind. So it is, to answer your question, these things are of interest to transmission system operators for sure.
Okay, because from our experience, we try to do it, at least I try to do it a lot with distribution system operators, and everyone says we are really interested, and when I really show the results and want to do a field test, they're like, okay, let's talk more about it. So they are reluctant to implement it on the system. Protection systems, forget about it. Even for control, they are not really active to do anything about it. So if you're talking about optimization, is it really feasible, or they really want to think about it?
I think they're thinking about it. Let's put it at that.
Okay, thank you.
One more comment on that, just briefly. I think you know this. I mean, in Germany, the process of introducing new redispatch regulations is currently going on, and this goes basically in this direction. So making flexibilities accessible to more parties or more grid operators that can use it, including DSOs. And I think maybe that's also a point why they are hesitant at the moment to look at other systems as well.
Hamid Zaripur, University of Calgary. May I make a comment about the previous comment / question? Okay, so I guess a lot of things that we discuss here, probably we always wonder who's going to use them. Are the utilities ready to apply them, implement them? And at the moment, probably the answer to most of it is no. But what I've observed based on my interactions with utilities, at least in Alberta and Canada, is that things are changing. Like PhD students, like some of you here, are being hired in those utilities. They are changing the paradigm. They are changing the discussions. I obviously see that the demography of decision makers in the utilities are changing. A lot more people with PhD degrees are working in power system companies and power utilities these days than, say, 10, 15 years ago. They are not afraid of working with innovation and universities and more sort of forward-looking things. So my comment is probably the answer to you is no, but that doesn't mean that we shouldn't push the envelope. That doesn't mean that we shouldn't work. Thank you.
Shmuel.
You know, we've been looking on the issue of how to mobilize flexibility on the demand side, for example, in order to help under provision of 2222, which is now one of the mechanisms, you know, one of the paths to do that. And one of the issues that comes up, for example, if you look at harvesting flexibility from water heaters, or from HVAC devices by curtailing them, or any kind of thermostatically controlled load, is that what's known is perhaps the nameplate of the devices that you are going to curtail. But when you aggregate them, at any point in time, you don't really know how much energy was actually consumed at the time of curtailment. And even if you knew you metered it, again, once you curtail it, you don't know how much would have been consumed the next 5 minutes because the device is now being curtailed. So the whole issue of harvesting flexibility and mobilizing it to create some wholesale market products like VPPs has to recognize that there is a lot of uncertainty on the demand side, and if you really want to have some credible bids to submit a VPP supply function, which we're developing, we have to start to think, take the approach, for example, that is used in operations research in revenue management. That's the approach that airlines are using to decide how much overbooking to do or decide how to allocate seats when demand is uncertain. So there is a whole literature, a whole area of bidding or submitting uncertain resources in a production process that have to be accommodated, and this community has to start to look at that approach, because we're really in a world now of uncertain production and inventory management and things like that.
Thank you. Any of the panelists want to comment on that?
Like I said, I want to say just a few words. Thank you, Shmuel, for the suggestion. We'll definitely look more into literatures in different disciplines, but we are our previous work to characterize the flexibility region. We're also taking into account of some uncertainties in distribution systems. So what we're trying to do is to characterize from a robust optimization perspective, given those uncertainties of some uncontrollable loads, how can the surplus of those flexible resources compensate for some unforeseeable, uncertainties from the uncontrollable assets. Definitely will result in more conservative, results. But I guess that's one of the ways to mitigate some of the uncertainties from.
Oops. Quick response. So we have one more question after.
Well,
that.
the point that I was trying to make is that somehow we have to think to borrow from other disciplines how to manage risk. In fact, ARPA-E has supported now, put $30 million in using risk management techniques, trying to learn from the financial industry, from any other industry, to recognize the problem that you're really trying to solve when you're creating those real options on hedges or physical hedges is a risk management problem. It has to be addressed as a risk management problem where you have a lot of actors, these ideas of centralized optimization under uncertainty work fine in planning, but when you are trying to create demand, to mobilize flexibility bottom up, then you have to use risk management theory and the techniques that are used in finance rather than the methodology that have been discussed here.
Okay.
Thank you, Shmuel.
Mads.
My name is Mads Almasalki, University of Vermont. I'll ask a related question. Could you talk a little bit about the role that baselines play in your work when it comes to flexibility? So that could be baselines, forecasts, renewable generation, any kind of baselines in your work related to flexibility.
Who wants to tackle that? We have a tough audience today. Claudio.
Claudio Canizares, University of Waterloo. It's a follow-up to Shmuel's comment about risk management. I think it's an interesting idea, but I'm concerned that when you're applying these economic theories to power systems, you have this underlying physical system you have to deal with. And that complicates the problem significantly. And this already happened with markets, right? in which we were playing all these games and then not considering the physical system, then you end up in a lot of trouble. But I think it's worth pursuing and understanding. However, with this caveat that you always have this physical system limiting what you can do, right? And some of these issues like robust optimization, you cannot really apply because you have nonlinear systems, you have to linearize them, you have to make all these approximations, and in that process, you know, you lose some information. Sometimes it works, sometimes it doesn't. So just a caveat that it's not a market, it's a physical system. And I see the same problem where you're looking at this P2P type of model. A lot of people in communications are applying this to power. Then when you look at things, there's no constraints. They assume that everybody can sell power to everybody and exchange power like it was an internet type of connection, and no constraints on the interfaces or what is happening underneath. And that's something that we need to be aware of.
Okay, on this, I think we should close this session and thank again our panelists and show our appreciation for all their work. Thank you.